clearly. I will show you. You cannot, if you plot your graph, if you're not using B-spline, if you are using only straight line, you can see what happened. Yeah, you can get a very not nice graph like this. Okay, let me show you some. If you are not you only using straight line, you will only get like this. Hello guys, Assalamualaikum warahmatullahi wabarakatuh, and a very good evening, I think. So today I want to make a video to clarify something that people in YouTube asking about a video on the differentiation method, which is Dunn method, for you to know the capacitive contribution and also diffusion contribution. I have show you a lot of step by step, but still a lot of question regarding the video. So this video is to clarify what you should understand throughout the analysis. So basically this is just introduction, very easy, and this procedure is a lot of people might understand. You can also run CV at different potential window. Not different potential window, different scan rate, 1 millivolt to 6 millivolt is up to you. You can, minimum is 5 millivolt. Minimum is 5 scan rate. For example, it's 1, 2, 3, 4, 5. It can go to 10 millivolt, it can go to 100 millivolt. It depends on you. For this step, I think a lot of you can get it and read the current response, the current density at which you fix the potential. In this case, I fixed at 0.37 volt. So a lot of people are asking how to read the current response. So let me show you for this step. So go to your origin, because you are plotting your graph on the origin. Okay, this is a different type of example I given because it's different paper. So let me show you some of the CV with different scan rate. Okay, so for example this one, and just draw a line, make a line, a straight line, and you can draw. This is the line. Okay, for example this is straight line, and just put here, and using here data reader from the origin, just put the data reader on the graph, then it can read your current response at 1 millivolt per second and so on. Okay, because of this material is not suitable at higher scan rate. As you can see, when the scan rate increase, you cannot even justify the obvious formation of the redox peaks. Okay, that's why it depends on your sample. Okay, this is the correct way to know your current response, just using the origin. You can also use the Excel if you don't want to use origin. It's up to you. Just put the cursor and you can see this is the data y-axis that we want to read for the current response. Okay, go back to our slide. Okay, this is our slide. So now you understand how to read the current response. Okay, next is the procedure. So we want to have a plot IV versus V power half, meaning that the current divided by or versus the scan rate power of half. Okay, so you can get this step to get what we call is the K value. Okay, K1 and K2 value. But for the step by step that I show you just now, we just want to get let me be sincere to you. You need to be what I call that consistent, and you need to be systematic. because what you need, let me show you some Excel. First, you need to have scan rate, current, and also this is current that I tried to teach you to read the current from the origin. And you also need to have log scan rate. This is easy. Log 10 power of current, you can get the log scan rate. And also we want log current, which is log 10 power of B2. Excuse me, for log scan rate is log 1, 2, 3, 4, 5. And for log current is the log that you get from the origin, your current response. Okay, this Excel sheet is important for you to get the B value. So I'm teaching you to get the B value first. So from the presentation mode, you can see that the B value is towards the end of the slide. So let me show you. Okay, this is the B value. You want to observe or obtain the B value first to signify whether your material is diffusion control dominance or diffusion limiting prominent, which one belongs to your sample. So after you get your B value, you need to get your R square value. To get the R square value, using the same scan rate, and just use the Excel to get scan rate power of half, and you must read the current anodic and cathodic. So go back to the origin. Okay, this ups belongs to the current of anodic because it's oxidation. So this is the current anodic, and to read the current of cathodic, what you need to do is you need to make another line. Okay, make another line and read the most obvious cathodic current. Don't read the cathodic current from the same potential, because as you can see, if you read from 0.35 volt, only the anodic is obvious, but the cathodic is not so obvious. Okay, let's say in this example, the most obvious one is at 0.4. Okay, this 0.4, the current response at anodic only. Don't take for cathodic. For cathodic, here, see the ones that most obvious is around 0.1 volt. So just take the data reader and read the value at each scan rate. Okay, so that's the trick. So next, when you get like this, then when you plot your data, you will get a very nice graph. I will show you a very good graph, which is the R square. Okay, this is the R square graph. Okay, then you can get the R square graph and determine whether your sample have a good R square or not. From the example I already show you, anodic and cathodic R square value close to 1 indicates that the material has a reversible capacity. So it's good. Okay, then we already know our B square, we already know our R square. Next, what we're going to tackle on is to get the key value, because from the key value you can get your contribution ratio, contribution percentage, then you can plot your Dunn real. Okay, so for key value, okay, at fixed potential, you can use the same potential to get a B value. So you have the O current response at oxidation or reduction. This is optional. You can use either the current response at oxidation or reduction. If you want to see the difference in the value, you can use both. Okay, that is the scan rate. The most important thing is to plot scan rate power of half, and the y-axis is your current response divided by scan rate power half. So next, we're going to see our key value. Okay, this is our key value. Okay, don't be surprised. Sometimes the intercept value might be negative. That's why you need to plot at different point, because at different potential window, the K value might be different. Okay, that's a little bit of limitation in this step. You try your best to get both intercept and slope a positive value. Okay, let's see what we got here. So when we got here, we already get our K value, because when you get your K1 and K2 value, which let me show you, which you know that you can get your K1 value from your gradient and K2 value from the intercept, then you can calculate your capacitive and diffusion contribution. So how to get that? Let's say you already successfully get your K value. So you go to contribution Excel. What you're going to do is, this is the K value and this is the K2 value. Okay, so to get the value of capacitive, what you need to do is you times the K1 value with the scan rate, because K1 times scan rate, you get the capacitive contribution. And to get the K2, the diffusion contribution, what you need to do is K2 value times with the scan rate. Okay, that is the diffusion contribution. Then you can get the percentage. It's quite easy. For percentage is K1V, the capacitive divided by capacitive plus diffusion times 100, then you get the percentage. Okay, so depends on how you tackle your paper. You can plot one by one. At scan rate 1, what is the contribution ratio? At scan rate 2, 3, 4, and 5, it depends on you. But normally, most of the paper, they just report on the bar chart, and they just going for only one sample at one scan rate. What is the contribution ratio? Okay, it's different. Okay, I think most of you get that point, but how to make it a Dunn real? Okay, this is a little bit tricky. A lot of people might mistake on this. Okay, let's go one by one. Okay, to get the Dunn real here, in this case, this is the Dunn real. This is different example. Okay, what you need to do is, okay, let's say if you want to do this, you need to read the data at each potential. Okay, what I mean by each potential, if your scan rate is 0 to 0.5, you need to start read from 0, and you need to end your read at 0.5. During the interval, you can read at 0.05 interval, or if you want to be most accurate, you can read from 0.01 volt interval. What I mean is like this. Okay, for example, if you are lazy enough, it's okay to read from 0, 0.5, 0.05, 0.1, and so on. How to read? Just click the data reader, and for example, at 1 millivolt per second, just read here. What is the value of anodic? And at 0.05 here, you will read the current response at both anodic and also cathodic. Okay, so I hope you understand that point. Okay, normally people say if you want to get a very accurate graph, you need to have like 100 points or even more than that. Okay, so if you do this technique, you might only have not even 20 points. Okay, like this one. I read from 0 to 0.5 is around 11 point only. So this reduction and oxidation is a normal graph without I convert it after the percentage contribution. Okay, this is what I read. This is a normal current response. For example, here at 1 millivolt per second. Okay, this is normal current response. And here, the percentage capacitive is after you times your K value with scan rate or scan rate power half. So this is your capacitive contribution. Okay, as you know that the capacitive contribution is the same because we are using only at 1 millivolt per second. So diffusion also the same. Okay, so the difference here is your R after and O after. Means that your current response after and oxidation, current response at reduction, and also current response at oxidation after you times with capacitive. Okay, this is the mathematical how it look like. Okay, for R after is D2 times B2. So percentage capacitive times with B2, the reduction. Okay, then the rest is the same. For our O after is percentage of capacitive times the times with the oxidation. So this is for if I want to plot for capacitive, and here H and I if I want to plot for diffusion control. So it's two different graphs. If you want only to plot capacitive, just use one. If I do like this, I can get a graph like this one. I will show you the graph of Dunn. Okay, this is the Dunn real. So if I'm doing like that, I can get two graphs for diffusion limiting and also diffusion. Or diffusion limiting is the capacitive, and also diffusion is for diffusion control. Okay, so when you connect the graph, so it will go like this. It will not go like this. Sincerely, I will show you. You cannot, if you plot your graph, if you're not using B-spline, if you are using only straight line, you can see what happened. Yeah, you can get a very not nice graph like this. Okay, let me show you some. If you are not you only using straight line, you will only get like this. It's very quite bad because you are go for interval 0.05. If you go for interval 0.01, it might have a very nice graph without the B-spline. So to tackle this issue, just go to the properties. Here, change to the B-spline. Okay, for this graph also, change to the B-spline. Okay, like this. So you can get a very nice graph. So I hope I answer your question. Hopefully there is no mistake during the analyzation and during the characterization. So hopefully you also can plot the Dunn method. So any question, please before that, please like the video and give some good comments on the video. So I hope you success on your method also. So basically I want to clarify this is what I'm trying to analyze and what I'm studying from YouTube, from papers. And if you know a lot more way how to plot the Dunn's method, it's very good to share the knowledge. And thank you very much. I hope you can like the video and also give a good comment. Okay, bye. Thank you.